Welcome to Optimizing Kubernetes Clusters on Spot Instances for Cost and Performance. My name is Ran Scheinberg. With me is Carlos Ueda. We are both AWS Specialist Solutions Architect for EC2 Spot Instances. And today we're going to talk to you about how to run Kubernetes worker nodes as Spot instances in your EKS clusters. This is the agenda that we're going to cover in this session. We're going to do a quick recap and overview of EKS and Spot instances. We're going to go over auto-scaling groups and how to use them as a tool to provision Spot instances for your Kubernetes clusters worker nodes. We're going to address things like handling spot interruptions to avoid impact on your application. Carlos is going to go into how to scale your applications using horizontal pod autoscaler and cluster autoscaler, as well as Taints, Tolerations, and Affinities. And we're going to go over some tools that will help you run production-grade Kubernetes clusters using Amazon EKS and Spot instances. Let's get started with Amazon EKS and go over a bit of what it is and how it can help you run Kubernetes on AWS. So Amazon EKS is a managed control plane, which takes away the heavy lifting of installing, operating, and maintaining a Kubernetes control plane. So you just get an endpoint which you can point your kubectl at, and then you get a full managed control plane for EKS where AWS handles the redundancy and upgrades in that control plane. You just need to connect your worker nodes that you run in your own VPCs into that control plane and deploy your applications on them. It's important to note that Amazon EKS is Kubernetes certified and has is fully Kubernetes conformant, so you can just use your existing tools and plugins that you have been using on your different Kubernetes deployments. Also, all your applications are fully compatible, so you can just easily migrate any application running on a Kubernetes cluster into Amazon EKS. Let's go quickly over how customers are using Amazon EKS today. The main use cases we see are microservices, and this will be for the applications that were more or less born in the cloud. Using container scheduling such as Kubernetes is a great way to run microservices in an easy way and help you get the resilience that you need. Another use case we see is customers building platform as a service around Kubernetes. So they just allow their developers to focus on their application code and not focus on managing containerized applications at scale. So they would build around the Kubernetes clusters tooling to just allow developers to push their applications into the cluster. A third use case we see is enterprise application migrations. This would normally be things like Java applications migrated from a data center in a kind of a lift and shift pattern into the Kubernetes clusters as they just get containerized and run on the cluster as they usually run. And a fourth very popular use case that we've been seeing is customers running machine learning workloads on Kubernetes clusters using Amazon EKS, and they would use things like Kubeflow in order to do that. So this was a very quick overview of Amazon EKS. Now let's get into Amazon EC2 Spot instances. Spot instances are one of the possible purchase options for EC2, where customers would normally start with on-demand instances where they pay by the second, and they start to define the workload's needs or use on-demand instances for spiky workloads in their applications. The second purchase option for EC2 is reserved instances, where you make a 1 or 3 year commitment against a significant discount to run your committed workloads and steady state. And you would run things like databases using reserved instances so you can save when running them. The third purchase option, and this is where it gets interesting, are spot instances. And spot instances are actually the spare EC2 capacity that we have in the AWS cloud. And we offer that spare compute capacity at savings of up to 90% off the on-demand price. It's important to note that spot instances are the same capacity and the same servers as on-demand. And the difference is that spot instances can be interrupted with a 2-minute warning when EC2 needs the capacity back for on-demand usage. That means that spot instances are good for fault-tolerant and stateless workloads. And when we start talking about Kubernetes workloads, we address the fact that a lot of customers are running microservices on Kubernetes clusters, which are normally very much stateless and fault-tolerant. So these make a great fit for containerized workloads, and we're going to dive into that later in the presentation. The way we see customers succeed the most with spot instances is by diversifying the way they use spot instances across multiple instance types and availability zones. Most of the people watching this session right now probably don't need a cluster of 1 million vCPUs, but we have a great example from Western Digital, which have been running an HPC cluster of 1 million vCPUs in order to decrease their job running time from 20 days to 8 hours. And this is when they're running millions of simulations on how they build their hard drive heads. And you can see in the graph that they've been using many multiple instance types in order to get the spot capacity that they need. If some of that capacity gets interrupted, the tooling will help them replenish that capacity from a different capacity pool so the jobs can continue running without having any significant impact on the availability or performance of the job. So while you don't need 1 million vCPU clusters, you can take away from this example that the way to be successful with spot instances is to be flexible around the instance type that you want to use for your workload, and to run those fault-tolerant workloads across many different instance types. And when we start talking about Kubernetes, it's fairly easy to run similarly performant instance types from different instance families in EC2 in order to use as worker nodes and spot instances in your EKS clusters. Let's dive a bit deeper into how customers are being flexible around the instance types that they use in their workloads and in Kubernetes clusters specifically. We have here an example of a C4 instance family running in a region with 3 availability zones, and the C4 instance family has 5 sizes. We can see that the spot prices can be different between the availability zones, and we can see that they're heavily discounted against the on-demand price. And these are just pricing examples, but we will show you how to see spot prices later on in this presentation. What we know is that each instance family, in each instance size, in each of our availability zones, in each one of our regions, is a separate spot capacity pool. So you already know that you can run your Kubernetes clusters across the worker nodes for your Kubernetes clusters across multiple availability zones, and that way you're unlocking more spot capacity from multiple capacity pools in the same instance family. But you can also use multiple instance families and multiple instance types to run your worker nodes as spot instances in your Kubernetes clusters. And that way you're unlocking much more capacity. And if you're well diversified, like we showed in the previous example, if EC2 interrupts some of your capacity, the impact on your cluster will be small because only a small portion of your instances will be interrupted, as opposed to if you would be running all your capacity on a single availability pool, single capacity pool. And AWS helps you achieve this diversification process using different tools. On the right, we can see an example from EMR, where the EMR instance fleets configuration option allows you to select multiple instance types, and EMR will select the best instance type for your workload to run in terms of availability and price of the spot capacity. If some of that capacity gets interrupted, EMR will replenish the capacity from a different instance type. We're not going to dive deep into EMR because that's not the purpose of this session, but I wanted to show you that we have different tools for different workloads on AWS to leverage spot instances best practices such as diversification. The far more relevant tool for this kind of workload for Kubernetes clusters is EC2 auto-scaling groups. This is the tool that we're going to focus on as Kubernetes node groups for our EKS clusters. As you can see in a screenshot from the console, we're able to select multiple instance types in a single auto-scaling group. This is a feature that we launched late 2018, and this allows you to follow that best practice of instance type diversification. We're going to show you how to create those auto-scaling groups for your Kubernetes clusters and bootstrap this diversified set of instance types as Spot instances into your cluster. Just a few more notes on how Spot instances work today. If you've worked with Spot instances up until a year ago, you would know that we would have price fluctuations and spikes. This is no longer the case. Price changes infrequently based on the long-term supply and demand of spare capacity. So there's no longer any price spikes, and you get a much more predictable pricing experience today with Spot instances. Another important change from late 2017 is that there's no bidding involved anymore in Spot instances. You don't need to bid for the capacity. You just request the capacity and pay the current market rate, which again is very smooth in how it changes the price, if it changes at all. So it's important to know that bidding is no longer a part of Spot instances. Interruptions will happen when on-demand needs the capacity back. So when customers launch more on-demand instances in the capacity pool where you're running Spot instances, your Spot instances could get interrupted. And with that, let's dive a bit deeper into interruptions. We know that generally speaking, less than 5% of Spot instances globally are being interrupted by EC2. And the work that you're doing to allow your workload to run on Spot instances is great for building fault tolerant and stateless workloads. Because if you're able to handle Spot interruptions, that means that your workload is fault tolerant and you're kind of cloud native in how you run your applications. So the work that you're doing also helps you be resilient and meet your SLAs. Technically speaking, there are two ways to catch the interruption warning in order to do things like checkpoint your work or drain from the ELB. In the context of Kubernetes, what we're going to show you is that you can catch that Spot instance interruption warning and use it in order to drain your worker nodes, meaning that pods will be gracefully shut down and rescheduled on other worker nodes in your cluster. This means that using the 2-minute interruption warning, you can make sure that the Spot instance interruption will not have any impact on your workload, so that you will drain the worker nodes and those pods will get rescheduled on other worker nodes. Before we dive deeper into how to run Spot instances as Kubernetes worker nodes, I want to show you a few tools that are relevant as you learn more about Spot instances. The first tool I want to show you is the Spot Instance Advisor. The Spot Instance Advisor shows you the interruption rate for the trailing 30 days. And the interruption rate means how many of the instance types in this region were interrupted when on-demand needed the capacity back. Generally speaking, we know that typically previous generation instance types have lower interruption rates compared to newer instance generations. So we can see that the C4 largest across all its sizes in the Oregon region had less than 5% interruptions in the last 30 days. If we compare that to the C5, we would see that some of those C5 instance types were interrupted between 10 and 50% or a bit higher than that even. We can probably see the same for the M4 instance types, and we can see that most of the M4 instance types were interrupted less than 5%, and the M5 instance types were interrupted more. So this is something to take into account as you select the instance types for your workload. The next tool I want to show you is the Spot pricing history. And this is where we allow you to see the last 3 months of prices per instance type per region for the relevant product or operating system. And we can switch this over to 3 months, and we can see, like I mentioned before, that there are hardly any price fluctuations. You can see that R4 extra large in EU West 1C availability zone in my account had very small fluctuations over the last 3 months. And if we take it down to a week, we can see that there were hardly any price changes in this instance type. And this would be relevant for many other instance types as well. And in many other instance types, we don't see any price fluctuations at all. You can use this tool in the console, or you can use it programmatically if you want. The last tool I want to show you for now is the Spot savings summary. And this allows me to see a snapshot of the current Spot instances that I'm running in my account. So I'm currently running 44 Spot instances, and I can see that the total amount that I'm paying for the hourly price of those Spot instances, and I'm tracking 75% savings of the on-demand price with these Spot instances. So this is a great tool to see what you're currently running in your account and what your current savings are. Let's get to why containers and Spot are a really great fit. So like we mentioned before, as you architect your microservices architecture to run on a containerized workloads and you're using Kubernetes on ECS, normally your pods or tasks will be stateless and fault tolerant. So this is a great fit for capacity that is actually interrupted and will allow you to get very deep savings of the on-demand price. We have a great example from a customer called Skyscanner, which is a travel fare aggregator. And a lot of their applications are running strictly on Spot instances. And we can see that they're tracking 74% savings over all the regions that they're running their Kubernetes clusters on using Spot instances. So this is a great example. And we have other customer examples here that are running containers using Spot instances on AWS. Let's get to the best practices that we mentioned before, and we're going to cover several things. We're going to cover how to acquire capacity, how to handle the interruptions using the Daemonset that will catch the interruption notification and drain the node. Carlos is going to go over scaling mechanisms and demo how to scale those Spot instances in your Kubernetes clusters. He's going to cover Taints, Tolerations, and Affinities. So for when you want to run workloads on demand or you want to slice and dice your cluster, and finish with some tools and takeaways for this session. The first thing we want to cover is how to acquire capacity. eksctl is currently the recommended tool in the EKS toolbox to provision and manage EKS clusters. And in the last few months, the tool also added support for managing and adding node groups. And like we mentioned before, these node groups are going to equate to EC2 autoscaling groups. So this is a quick example I have here in the slide, but I'm also going to show you an example from my actual cluster. And here I have my Linux environment. I'm going to show you the YAML file for my node group, and this is actually a way to define my node group as a YAML file and get eksctl to create this node group for me, which is actually an EC2 autoscaling group. So I can see the name of my cluster here and the region where I'm running it, the name of my node group, and I'm going to start with 20 instances and with a min size and a max size of 20. Like we mentioned before, I want to diversify my Spot instances across several instance types. And here I actually selected instance types that have the same amount of CPU and memory, so it will be easier to manage the capacity in my cluster. We have multiple instance families that allow you to do this with the same amount of CPU and memory. There will be some performance variability, but many workloads that we see for customers are able to handle that workload, that performance variability, and they are okay with that flexibility in order to unlock savings of up to 90% with Spot instances. Some other configurations that I have for this node group, which will go into my EC2 autoscaling group configurations, is optional amount of on-demand instances that will run in this autoscaling group, as well as the ratio of Spot and on-demand instances to keep at all time. And the Spot instance pools is an important parameter here because this tells autoscaling group how many of the cheapest instances per availability zone it should fulfill capacity from. So since I selected 6 instance types for my autoscaling group, I want the autoscaling group to bring me that capacity from all the 6 instance types. I can specify a lower number here and keep the, for example, 4 cheapest instance types from each availability zone. But I'm going to go with 6 because I want to be as diversified as possible with my workload. So if one of those instance types gets interrupted in one of the availability zones, only a very small portion of my instances will be interrupted and they won't have any impact on my workload. The last configuration I have here is a label, and all the all the instances in this auto-scaling group is going to be started with a Kubernetes label of lifecycle equals EC2 Spot. I'm going to label them like that in order to deploy my Spot interruption handler Daemonset only on those Spot instances, so I can make sure that I'm not wasting any CPU or memory in running that Daemonset on on-demand instances because it's not required there. I'm just going to call a command for eksctl to create the node group with the configuration file that I just showed you. And eksctl is going to go ahead and create this by creating a CloudFormation stack and deploying this auto-scaling group to my account. Instead of waiting for this to finish, I already deployed an auto-scaling group, a node group with this tool and this configuration before. I'm going to show you how this auto-scaling group looks right now in my account. This is the current auto-scaling group that I have in my account with the same configuration. And you can see the instance types that I configured in my YAML file. The spot diversity, the number of pools that I mentioned in my file is 6. As I described, I have no on-demand instances here, and my desired capacity is 20. Let's go to the EC2 console and see exactly what kind of instances EC2 auto-scaling group brought in for my Kubernetes cluster. So I'm just going to filter by the name of this auto-scaling group, and I can see that in each of my availability zones, I have a nice diversified set of instance types, so I can implement that best practice of diversification. So right now, these are all Spot instances which are running as worker nodes in my Kubernetes cluster in a very easy to accomplish way. I just provided this configuration to eksctl, and it bootstrapped all these Spot instances as worker nodes to my Kubernetes cluster. Great. Let's continue with the presentation. The next thing we want to cover is how to handle the interruption. And we have a ready Daemonset for this that you can deploy. We have instructions for this in the EKS workshop website, which Carlos is going to show you later on. And this Daemonset has a very simple script running in it. It's going to poll the instance metadata for the spot termination time. And once it sees that the instance is going to be interrupted, it's going to drain the worker node in order to get all the pods to gracefully shut down and be rescheduled on other worker nodes in my cluster, which are still running and are not going to be interrupted by Spot. You can see the node selector here. So like I mentioned before, I'm going to only run this Daemonset on Spot instances in order to avoid running these on on-demand instances. Let's see the configuration for the Daemonset. And I can see here the node selector that I showed you in the slide, and these are only going to be deployed to my Spot instances. Let's deploy this. Great, so I deployed the interruption handler into my nodes. And now I can just see that my Daemonset is running on all the 20 Spot instances that I have in my account using the node selector of lifecycle EC2 Spot. So on all my EC2 Spot instances, I have this Daemonset now. If one of them is going to be interrupted, the Daemonset is going to catch the interruption, drain it, and avoid having any impact on my Kubernetes cluster. And with that, I'm going to switch it over to Carlos to go over the rest of these best practices and recommendations with you. Carlos.
Thanks, Ran, for handing it over to me. So in this other section, as Ran pointed out, we'll check scaling mechanisms for your Kubernetes and EKS clusters. For that, we'll check two different controllers that Kubernetes and EKS provide for scaling your application and cluster. The first one is the horizontal pod autoscaler controller. Horizontal pod autoscaler scales up the number of pods for your application. So you define a rule for your application to scale based on a specific metric. So that metric can be CPU, memory, or for example, number of message in an SQS queue. With that, the horizontal pod autoscaler will make a decision on how many pods are required and instruct the replica set or the deployment in Kubernetes to increase the number of pods. That will make your application to scale according to elasticity that is required. The second controller that we'll use to scale our application and cluster is cluster autoscaler. Cluster autoscaler is used to scale up the infrastructure part on the cluster. So effectively, cluster autoscaler check what pods cannot be scheduled due to lack of resources, which pods are in pending state, and based on that signal, it requests more capacity to the node groups and the auto-scaling groups that Ran has just shown. For that, I'm going to show you a demo where the first thing I'm going to do is just submit some request to my application. Let me show you the application and what's the configuration for that. So I just wrote an application. If I refresh that page, you'll see that it will take some time because it's using CPU, and I'm using a CPU metric on the horizontal pod autoscaler to elastically scale my application. When my application returns, it will come back with the approximation of pi using a Monte Carlo simulation. So you see that it's still waiting. My application has been deployed through code pipelines. And when I'm deploying it, I'm defining what is the horizontal pod autoscaler rules that I'm applying to it. So you see that as part of my continuous delivery, continuous integration mechanism, I'm also defining as well how would I like to scale my application. Right. Let's go back to cluster autoscaler and how cluster autoscaler gets configured. So once that I scale my application based on those metrics that we just mentioned, the CPU, for example, or the memory, the next thing that will happen is that as capacity is required, as pods are requested, there will be some of them that will stay in pending state because there's no more capacity on the cluster. Cluster autoscaler is the component that will read that pending pod signal and increment the capacity on the autoscaling groups and node groups that Ran just mentioned. The configuration that you see on this slide points to two different autoscaling groups. So this is the name of the autoscaling group as well as the limits for those autoscaling groups. That 320 means 3 for a minimum, 20 for a maximum, and the name of the autoscaling group that we would like to include for increasing capacity or decreasing capacity. You see that we can get more than one autoscaling group and node group added for cluster autoscaler to decide how to scale our capacity for the whole cluster. Cluster autoscaler makes some assumptions on all the nodes within a node group, within an autoscaling groups, having the same number of CPU and memory. We can still implement diversification by creating multiple of these node groups and autoscaling groups and making sure that the selection of instances that we apply, the diversified selection of instances that we apply in that node group has a similar number of cores and a similar number of memory. But the message is still that we need to implement diversification across all our configurations just to make sure that if our pool dries out, we get a minimum impact to our cluster and we can still recover capacity at scale. With that, we're going to move to Taints and Tolerations as well as Affinity. So applications may have a different risk appetite and risk profile. Some applications that are fault tolerant are great for spot instances, but we understand that some applications may still be refactored and still may require a bit more work to make them fault tolerant. In Kubernetes, we can apply tolerations to make sure that only the applications that tolerate spot instances, and by that what we mean is that they are fault tolerant and can benefit from those instances, will run onto the spot instance part of the capacity that we requested in those node groups. This makes sure that the other part of the application that are perhaps not so fault tolerant, will never run on the part of the cluster that will have terminations due to spot interruption notifications. We can also apply affinities, and affinities can be applied in many different ways. The traditional way for multi-tenant cluster is a slice and dice and making sure that only specific application run on specific node groups. But they can also be used, like is the case on the bottom left code snippet, where what we want is to apply some best effort affinity, some preference in practice to a specific set of capacity. So in this case, we've chosen on demand, so we can make sure that our application will, as much as it can, run first on demand, just to prevent those instance termination notifications. We can flip over this decision and say, before anything, I would like to, as a preference, would like to run as much as I can on spot instances to optimize for price. So the selection is yours based on the risk appetite that you decide for your application. And if you are optimizing for cost or you are optimizing for reliability with no interruptions, spot instances will be still equally available for you for as long as you have implemented these techniques that just Ran mentioned on diversification and so on. The next aspect that I would like to show is tools. So the first one is EKS ECTL. EKS ECTL is the official tool that we go for CLI to manage EKS clusters. The other tool that I would like to show you is CloudWatch Container Insights. CloudWatch Container Insights is still in preview, but it's a great tool to show you metrics and logs from your pods and applications. Let me take you through a quick view of the example that we just showed. So if I go back to the console and in metrics, you can see a new section with CloudWatch Container Insights. You can, based on the metrics that CloudWatch Container Insight is populated from your cluster, create dashboards that are relevant for your application. So in this dashboard, what we'll get is how our application, when we started it, is scaling up the number of pods, showing how the horizontal pod autoscaler and cluster autoscaler are requiring more capacity as requests are coming. CloudWatch Container Insights also will help you with logged insights to check what are the logs that are relevant for your application. So for example, I can just edit and pick up for the cluster autoscaler when scale up events came back into my cluster. So you see, those events over there are showing when the cluster decided to scale up my application and cluster. The rest of the tools that I would like to show are tools that people that are running with a Spot in production are also using to manage their Kubernetes clusters. So the first one is the cluster scheduler. Kubernetes does only make scheduling decisions when new configuration is applied. Cluster Scheduler is a Kubernetes incubator project that reevaluates those decisions based on configurable rules. The second one is the Amazon or AWS Kubernetes node drainer. There are other situations aside from spot instance terminations where, for example, auto-scaling groups scaling in due to rebalancing on availability zones, where your pods need to get an interruption signals and be drained accordingly. Kubernetes node drainer takes care and automates all those actions to make sure that your pods shut down gracefully. Last tool that I'd like to mention is the cluster over provisioner. Cluster over provisioner will help you to allocate some headroom to make sure that when you get a peak of requests coming, there is still enough space to react quick enough and allocate capacity. It uses low priority pods that will be preempted when your horizontal pod autoscaler rules require to scale up the number of pods. And with that, I would like to take you through the main takeaways from this session. So the first one is understand the Spot best practices. These apply not only to Kubernetes, but all the workloads where you would like to apply Spot instances and reduce the cost on your infrastructure. So remember about the pricing model, the long-term supply and demand, how to apply termination. So we've seen the Kubernetes approach, but you also have CloudWatch events to handle the termination events. Remember the message of instance diversification. This is the best practice in some of the things that you need to bear in mind when applying it to any other type of workloads, and how to compose your fleet using a Spot Instance Advisor. And in the end, when you apply all these techniques, you can remove all the heavy lifting by using launch template and auto scaling groups. You don't have to do or implement this by yourself. Now, if we move to how these best practices apply to Kubernetes and EKS, you've seen how to apply instance diversification in the cluster autoscaler configuration and in the way that you acquire capacity. You've seen how to scale with horizontal pod autoscaler rules and how to scale the capacity as well with the cluster autoscaler. You've already seen how to implement a Daemonset to take care of the termination signal and how to apply Taints, tolerations, and affinities to define what is the risk appetite for your application and which part of your cluster is suitable for different type of workloads, including the Spot. Finally, we recommend you know your tools. These projects are changing every now and again, so you should keep an eye on cluster autoscaler and eksctl. Very often you'll see that every couple of weeks there will be some new functionality that will help you to reduce the heavy lifting. We also produce a roadmap that is available for anyone using containers and is open in GitHub. We recommend you to follow that and check what is that excites you from our roadmap. I'd like to leave you with these three resources. The first one is the definitive guide to running EC2 Spot instances as Kubernetes worker nodes. We're trying to capture all these best practices as they move over time in that particular blog. So keep an eye on it. It's a 20-minute read, and I'm sure that it will be engaging and you'll like it. We also have a couple of workshops. One EKS workshop, where we go through not only all these mechanisms, but quite a lot of other modules that you can explore. An EC2 Spot instance workshop, where you can explore not only how to apply Spot instances on EKS and Kubernetes, but also on autoscaling group, Elastic MapReduce, and other products that we offer covering other workloads. And with that, I would like to say thank you. Thanks for your time. I hope that you enjoyed this session, and I hope that you will be looking forward to complete some of those workshops. So happy coding and thanks.